Okay, I'm going to continue the second part of your Newtonian mechanics, okay? So second part, we're going to continue from this example 5.2-1. So here you are given three situations here, okay? So which of the following particles, so here particle 1, particle 2, particle 3, and you have to decide which one of them, okay, is in equilibrium, all right? So when you look at it, you have just one force, and here you have force 1 and a force 2, and here we have force 1, force 2, force 3, and we have a 60-60 angle, and we have no idea, but there is some particular angle right there, yeah? So when you look at this, you know that there is a single force. That force, okay, can be able to make this mass move because it doesn't have any force that is going to push it so that it won't move. Here, this force has the equal. See, equal, I said it equal is because of the length of this arrow, and it is the same thing. Yeah, so if you draw from here to here backwards, you're going to see they cancel out. So therefore, even though you have two forces acting on a mass, it's the same as the mass has no force because these two forces cancel each other. Yeah. So therefore, it won't move and it is in equilibrium. This thing, the same thing. You have this force and that force is going to cancel, and you have also this force, but it is completely okay. Look at this, going downwards. Yeah. And by this situation where there's two forces, okay, acting as a 60-degree, and this is going to cancel, all right, this a force, a downward force on that, all right, mass. Okay, why? Because it's kind of like a supporting, like a, see that the triangle like that way. Okay, so if you see it geometrically, you're seeing that, okay, which is of course being balanced, all right, this way on this symmetric. Yeah, symmetry is very important in the existence of everything in this multiverse or universe that we know, okay, to the limit of, course, human intelligence, is because they are in balance, all right? If the universe is not in balance, we're gonna be sorry. Yeah, so the other theory that we know, why are we here and we are living here and the universe is always the same. It doesn't really change that much. Everything that we know, the changes happened on the earth, is because of the time of the universe is so huge that our existing compared to the existing of the universe is very small. So therefore we cannot be able to understand the movement of the universe, okay, because it's too huge. So therefore the change that happened in the universe, we cannot be able to understand it because our existence is too short compared to the existence of the universe. Okay, we can't feel it or experience its emotion in it. That's why, do you ever hear the sound from the universe? No, it's silent, yeah? Because if we can hear, we will be so sorry, yeah? And it's going to kill us. The sound of the universe is so secretive. It's very discreet. You can't hear it. It's been protected. Again, life, again, okay? Life is a system, and it has its own protection, right? I would say inherent protective system. We're born with it, okay? Our system protects itself, and you recognize that, okay? Because you have a generated mind. Your mind's been generated like your acceleration. You have a mass, and there is a force, and then you have an acceleration on that mass. Same as that. Our system, life is a system, and that's just like your mass, right? And your mind is being generated from all the motion that your nervous system is making, right, inside of your mind. Okay, I would say the consciousness, right? So consciousness is something that's been generated constantly from your body system. So anyway, and they are in, again, equilibrium. Yeah, everything that we know is still in equilibrium and is very essential to our survivability. Is because if that equilibrium breaks, we will be sorry. Yeah. Okay, I'm going to make it shorter, shorter lecture video, so that way you don't have to, torture yourself to listen a long time. So anyways, but then, of course, it's better to listen to the explanation by the professor, because we study so many years, to understand these things. So my knowledge about this subject is way more than you are. Okay, I hate to tell you that, but yes. So if you listen to the professor, you definitely get a lot of the information. Of course, now the world is very discriminating, so you just want to discriminate me because I'm not you're not the same race from you, or something like that going on, right? You do look down on people who are not from the same race, because we're not speaking your same language as a native language. So whatever that is, just get rid of that. Okay, so every person who study a subject more than 1 year, they have something in their brain, they know. Okay, because they spend a lot of time in understanding these things. So make sure you give some respect for that to the professor who are not of the same race from you. Okay, all right. um, so when you look at it here in this example, you have the particles, the here and then here. Of course, we have D and E here, and we have to, of course, identify which one of them are in equilibrium. So when you look at it, we see this, and this one is in motion and is identified that with this little arrow going in motion with dot line, meaning like the position is changing. Since position change and we are observing this activity in a particular time interval, then we have a velocity. So since it is a very, showing you constant, meaning like this thing is moving in a motion with a constant velocity. So therefore, with the Newton first law, it is in equilibrium, because there are no external forces that is going to break that equilibrium or disturb that equilibrium. So here, when you look at it, this thing, okay, look at this, path. This is very straight line. Okay, this one is a rotation. Why? Because it has see, like the circular path right there. So this is a circular path. The particle is going, and of course, this little arrow is showing you the velocity vector. Going that direction. Your velocity, meaning like every time this thing take a different position on this, all right, circular path right there, you have a velocity, but that velocity is going in a constant, meaning like you do not have an abrupt or instantaneous change of the velocity, even though it is going in there. You have to understand, since you turn the angle, see, like the angle is changing all the time. So it's not a pure translation anymore. There is a rotation aspect in it. So therefore, there is acceleration. Meaning, even though we have a constant velocity for the linear, component of the velocity, we still have the circular velocity. Okay, we still have the circular velocity. And you got to understand another aspect of the velocity. I'm just going to write it in this way. So this is a circular velocity, and that angle has been changing. So therefore, you do have acceleration. Okay. All right. So here another thing. So you are swinging a weight. Okay, you're swinging a weight like that. Swinging, and on the end of a string around your head, at which point you let it go. You swing it, and then you're gonna let it go. So here already, a diagram, a pretty good diagram is showing you that you're swinging a weight on the end of a string. So the weight is right here at the end of the string, this guy, and you down there, of course, and you swing it, and then you're gonna let it go. So now the question is, which of the following path best approximate the direction the weight is going to travel? Is it going to go off that way or off this way, that way or this way? So you got to understand where is your force, right? That is going to give that motion. So you got to understand, like, since your force is coming this way, and the motion is happening in this direction, and if you let it go, it's gotta go according to that direction, which is tangent to that circular path, so therefore it's got to be this guy. It can't be that, can't be this or this. Okay, that is correct. Then we will go into second law. So again, go back to this Eureka video again, and in this Eureka, so we already did the mass, weight, inertia, and then we get into acceleration. Go to the same YouTube and you're gonna find that. I don't have to do this again for you, okay? You can do this. And then of course the inertia, review, resistance, the change in motion, So here is a picture. Oh, time to get up. I don't want to get up because I'm comfortable in my bed. I want to continue to sleep. Inertia, here's a little butterfly flying, And here's a big inertia. Is because of this truck, having a load, meaning like a bigger mass, So anyways, you can be able to see, it doesn't matter what object and what form they've got, that they are just a mass, And then of course, they're in motion, they're in rest. And inertia is it resists. You have a tendency to resist to change in motion, meaning like you have a tendency to resist, external forces. Okay, the second law, a body acted on by an imbalanced forces. Now we're gonna break that equilibrium. So the first law is equilibrium. Body in equilibrium, whether they're at rest or in motion, is going to maintain that state. The second law is now you've got imbalanced forces. Okay, if you have imbalanced forces on a body, it will accelerate. Okay, so that's, we put it in this way. Here is your body. You have imbalanced forces. Imbalanced forces meaning like the sum of the forces. You don't have just a single force. You have many different forces on that object, and it's going to have an acceleration, meaning like it will be in motion. And we write it, of course, in a mathematical equation. So the amount, so we gotta know how much of this, mass is how much of that amount, okay? The amount of acceleration, okay, is going to inversely proportional to its mass. Why? Because the physical thing, all right, in this phenomenon is only your object, which is your mass. So you have to understand, how much of this thing is going from one position to another, having a velocity, having an acceleration. Okay, what is this amount of acceleration? You have to calculate it. What is this thing that is describing this motion? And you can calculate it by doing your algebra on your mathematics equation. Mathematics is a very powerful language, because we can be able to describe many things in a very, very compact way. So if you want to know the relationship between this and that, you gotta move around. So when you move it around, you get this, okay? And suppose you have a constant force, okay, this is mathematic calculation, by the way, you're gonna get this, and that's what we call it. Acceleration is inversely proportional to its mass, okay, coming out from your mathematical algebraic operation, by taking out the function of interest, and then looking at that function of interest, the magnitude of it described with the other function. And of course we are taking one of the functions in the operations or in that equation as constant. Here I'm making my force constant, so therefore you can get rid of it and replace it with 1. So 1 divided by mass is actually inversely proportional to the acceleration. So now we can predict the amount of acceleration is, okay, inversely proportional to the amount of mass. So meaning if your mass is really big, your acceleration is small, and if your mass is very small, you are going to accelerate fast. All right, got it? So the bigger don't go fast is where it comes from. Now we are getting into mathematical expression, and this is your second law equation. And people usually write it this way, especially the high school teacher are going to do it, and they always ditch, all right, the sum. But this is very important, so make sure that you understand that you don't have a single force And if we do this, this force is actually representing the resultant force, okay, RF, which is a resultant force. So is this a scalar or a vector? So therefore acceleration is a vector, force is a vector, meaning like the mass, right, got to go in a motion to a particular direction. Yeah, so therefore we have to understand that we are definitely, okay, studying or analyzing the vector of that mass because it is going in a motion towards a particular direction. Yeah. And so here I'm just going to write the force that is causing this mass, okay, into motion. Yeah, and it is going with a particular acceleration. The acceleration is going to be fast if this mass is small. Acceleration is going to be slow if this mass is big. And then, of course, we are going to come down into this situation where you understand that it is sometimes helpful to break up the equation. Yeah, so here is the equation, and here is our general equation, and then we're going to break it up into x's. Yeah, so we have our x-axis, y-axis, and then z-axis. The very first two x's, we are going to break that force down into x and y. Yeah, meaning like we are going to study the particle in this, all right, coordinate axis and in this coordinate line. Yeah, there's two lines, so x and y. So we can be able to measure like how the particle is going, how many units it is going. Yeah, if you think about the space in the 3D space, you know that at what angle from the x-axis or y-axis, or I would just say like from the x line or y line, how much of the angle is it far away that this motion is happening. Okay, so when you look at it, we have the component of that force, starting to call component for everything that we analyze on the x line. We call it the sum of the forces on x line is equal to the mass. Our mass doesn't change because it's the same particle. And then of course we can break the acceleration down into on that x line. Yeah, and here this is a sum of the forces on the y line of that object mass, and then of course on the y line with the y force is going to go with the y acceleration. Okay, but it's the same mass, by the way. You're just describing the location of that, yeah, and where it is on the x-axis and where it is on the y-axis. So if you look at it here and my particle is here, I am on 2D again because I get rid of my z-axis. So I can say like this, like this mass is about, like 2 units and 2 units away from, okay, from the y-axis and the x-axis in this space. See that? And of course your resultant, which is this guy, okay, is going to go that direction. And when you look at it, you can be able to see like this. So here your force, if you think about the force, that is y, and if you think about this force, that is the x. Okay, again, I show only one, and that is a resultant, by the way. Here, look at that. Even on the y line, you have a sum of forces on y, and this guy, sum of forces on x, and that is the sum of forces of this and this. Okay, so suppose if you have like 3 forces on x line and 2 forces on y line, you're basically thinking about 5 forces, all right, on the whole thing. Okay, all right, we're on the same, all right, second law. And when you look at it, we already understood about this resultant force. We understood that we can break it into x and y component. We understood that many forces on x and many forces on y can happen. Okay, so these are all the sum. Yeah, some of the forces on x, some of the forces on y is going to contribute the sum of the forces on that mass, right? And it is going with the resultant acceleration, and that acceleration can be broken down into acceleration on the x-axis and acceleration on the y-axis. So we're looking at this 2 in this acceleration. Okay, so when you look at it, you got to understand this 2 thing. Okay, what is going on X and Y. Of course, we have actually 3x's in 3-dimensional environment. Right now, we're still on the 2-dimensional environment, flat on that plane. So what direction will the acceleration always be in? So now you gotta understand, since we have a resultant acceleration, we have to come up with, what is the resultant acceleration direction? So therefore here, here is your mass, and here is your first force, and here is your second force, and here is the combined force, and you got to know this is a combined direction of x, of actually mass m, and this is your acceleration. So this acceleration is of this mass because of that force. The forces can be broken down into this and this. So you have this direction and that direction. So if you think about the vector, combination, all you have to do is, if you start from this point, you are going to go into the second vector is this. Therefore the resultant is the starting vector, point of the initial point, starting point, and then the ending vector, or the end point of the second vector. So this is your first vector, and this is your second vector, and this is your resultant vector, and it's showing you the direction, and that direction is going this way. Why? Because you start to there, and then you go there, so therefore you initiated here, and you ended up here. Therefore, your direction is going this way. Meaning the mass, because of the forces acting on it, will move in that direction. Not in that direction and not in this direction, but in this direction. Because you have two forces, one push from there and the other push from there. So if you push from here and there on an object, the object is going to move this way. I think you should practice by going to the bar or something, and there is a billiard, a place where you can be able to use a stick and and hit it, and you pay attention to how your ball is gonna go. So use the ball and hit another ball. So you can ask your friend to hit it on this side, and you hit it on this side, and you're gonna see like your ball is gonna go that side. Depends on the energy that you put to make that force on it. So the equation resulting for the application of your Newton's second law, and we call that with this name, and that is the equation of motion. So meaning like the equation, and that equation comes from Newton's second law, and we called the body's equation of motion, which is actually, let me go back. All right, this one. Don't forget the components, by the way. Alright, the next example is a go-kart, which is this guy right there, and it's being pulled by two forces represented with this little two arrows as shown in the diagram. So the wheels on the go-kart, so here is the little wheel right there, it's going to allow that car to move in any direction without restraint. So now here you have four a situation right there, and you have to list them in order, from the largest to the smallest. So the magnitude of the acceleration of the go-kart. So now we're going to concentrate our list, and we're going to take a look at the magnitude of the acceleration. So our concentration is on the acceleration aspect of the motion, and we're going to list it in order. So now when you list it, you have to pay attention, to little forces like this. So you can go like this, and then you know that it is going this way. You can go like this, and then you know that it is going that way, and then you can also go like that, and you know that the resultant is going to go this way. So that's the first thing I do. Alright, to get the resultant or the final force. This is C, the resultant is here. So therefore, by looking at the A, B, C, and D condition, I have come to this and this straight away, because that is C, like combined, going to the same direction. So therefore, you're going to have the largest is D. The smallest one is going to be this guy, is because see like how the forces are acted on this object, in opposite directions. Therefore, every time your forces, external forces, are in opposite direction, they cancel. Yeah, so therefore this amount will be cancelled out of that force. So you're left with just a little force. So therefore we have identified the largest and the smallest. So when you pay attention to this guy, the situation A and B, you saw that the angles are, the first thing I noticed is the angles are the same. So therefore it's either going in this direction and in that direction. Directions are different, but the weight, okay, of the force, meaning like the weight, meaning like the amount of the force, is the same thing. So whether you applied it that way or you applied it this way, they're the same thing. So therefore they will go A and B, will go to the next order, the largest followed by A and B, and the smallest is C. So this is how you solve a problem. Alright, the next one is if no external forces are applied on this thing, the space shuttle shown here is gonna drift, meaning like it will go in a motion in a straight line from point A to C. Okay, it's gonna go from here. Every time we describe a motion, we always have a starting point and the end point and the path that this motion takes place. Then we're going to continue halfway, going halfway between that 2 points, A, all right, I'm going to go back here, see A all the way to C, and then halfway is a B, and the engine is going to engage us, meaning like the engine is on up to the halfway, and that is going to produce a constant thrust. It's just a motion or a force that is going to be perpendicular to the line drawn between points A and C. Okay, so when you look at it, it is perpendicular like that. Now this is not perpendicular, and then this is not perpendicular, but the condition right here, it is showing you that it produces a constant thrust, and that thrust is perpendicular to the line drawn between the points A and C. So this line, so your thrust is going that way. And now you are represented with this problem, well, which of the following trajectories here most accurate represent the motion of that space shuttle. So the engine is going to engage up to the point B, halfway, and your thrust is perpendicular, and you have to choose which one is the trajectories. Trajectories mean the path that this spaceship is going to take. So we have to understand the thrust is going perpendicular like that, and you're going this way, okay, and then this way, because your thrust is at 90 degrees to the line. So the first motion go from here to here, A to B, where the engine is going. So your motion is going to go, resultant is going to be that direction. See that? So all you do is the starting point, and then of course the end point is going to be here, going that way. So therefore you will draw like this, and now you see that this is a parallelogram geometry. So this and this is the same thing, so you can show with this little arrow because it's the same thing, the same magnitude, and the same direction. So you can build your resultant all right, trajectory this way. So you know that it will go that direction. Why? Because your thrust is going in this direction. So meaning that you have two forces acting on this, and what is a resultant? And the resultant is going this way. Okay. As the space shuttle moves from point B to D, now we're gonna go from here, and then this is a combined, right? So now we got to understand many different conditions here, and we are going to concentrate on the speed of that space shuttle. So when you think about the speed, you know that it can't be constant because the path changes, because you are just subjected to a thrust at 90 degrees on that object. Okay, increases at a constant rate. That is correct, because when you apply this and this, right, thrust is there, and you're going from here to here on a constant engine rate, you are going to increase the speed, all right, but at a constant rate. And the next one, this one, I'm gonna just like temporarily wait for the to analyze the other conditions. So increases for a short time and then remains constant. That can be true, because your engines is constantly going from A to B, and your thrust is applied, horizontal. It doesn't matter here or here or here. It will be the same. So therefore, it can't have an instantaneous speed for a short time. Just can't. And then decreases at a constant rate. It cannot decrease, because if it does decrease, it won't go to the point C. I mean, like, it won't take distance going that direction. It will come back down if you have a speed going down. Okay, and then the speed decreases for a short time and then remains constant. Again, if you have a decrease in speed, you will not move in that way. You will come back down a little bit. So therefore, your best bet is this situation right here. Increases at a constant rate. That is correct. All right, then we go to the point D, and then your engine is going to completely shuts off. You're going to turn the engine off. You come from point A to B with the engine, you got the thrust, and you move that way. And when you get to the point C and then you go to the point D, you're going to turn off the engine. So then we got to, of course, identify the path again, trajectories. Accurately represent the motion of the space shuttle after the engine is shut down. So after that D point, what is going to happen? So if you think about if you shut the engine off, right? If you shut the engine off, it will go in motion, is because you're just when you think about the space shuttle, what we're trying to do, putting the engine on, is to get out of the atmosphere of this of our Earth, like atmosphere layer. So we hit it. We hit that the space shuttle, to go to take a distance out of the grip of that gravity. Once you get it out, you can shut the engine off and it will go. And of course, it's gonna take the same trajectory, because that's our target is. You're not targeting straight up. It can't be, because there's a thrust opposing that, and you have two forces in there. And then it cannot curve, because it is keeping going with a constant speed. It cannot curve that way either, because it is going with the constant speed. And it won't go straight, because again, the situation in one, you have your thrust 90-degree, and then the engine, okay, which will turn off at D, but still up to D there was a force, which is your engine going that direction. So this cannot happen. This cannot happen, because you have a constant velocity. So it's got to keep the same trajectory. Yes, correct. All right, then after that point D, the space shuttle speed again is going to be constant. Why? Because we've been traveling with the speed, constant speed. All we did is to save the engine, but the push on that space shuttle up to the point C is going to give it enough force for it to go beyond the atmosphere. So I don't like this question, because it doesn't mention the existence of the atmosphere. All right, well, the medium is off, but actually the medium also is very important. Okay, the air resistance, because your engine is going to give enough force to get out of that atmosphere. Beyond that point, it's going to be constant. It cannot increase at a constant rate, no, because of the thrust and the initial force. Increases for a short time, no. Decrease at a constant rate, no. Decreases for a short time, because of this word, it can't happen. Yes, so it's going with the constant in this same direction. Then we come to a truck, and that truck drives along a horizontal road with a constant velocity. So motion is retarded, meaning like it's not it's just showing you how it goes, how this truck is going, and eventually halted means stopped by a set of crash barriers, because of these barriers gonna stop. and this car is going to crash into it or collide it. And the amount of barrels and sand within the barrels arranged in such a way to decelerate the truck at a constant rate. Because of this resistance, and that motion cannot continue. Why? Because some of the energy, coming with this motion will be absorbed by this barrier. So when you look at it, the 4 test run 1, 2, 3, 4, and we're going to experiment that, and we're going to look at the velocity and the mass of the truck. They are different, 10, 14, 12, and 8 here, and each of the following situation, A, B, C, and D, the barrels right here is going to stop the truck, in the same amount of time. So the only thing that is the same is the time, meaning like it is going to stop that truck, and then your question is asking you to put it in order, rank it, the force required to stop that truck, for the following situation, and we're gonna go from greatest all the way to the next. Okay, so when you come to here, you have A, B, C, and D. And when you see this very, very carefully, you see this is 10, 14, 12, and 8. So when you look at it, this is the smallest. Look at that. Velocity or speed, meter per second, meaning like going in a second, 8 meter, 14 meter in a second, 10 meter in a second, 12 meter in a second. So this is the slowest velocity that you can see. Then pay attention to the mass of the truck. That's 15, that's 10, and that's 10, okay, 100, and this is a 2000. So meaning like 2000, 1000, 1500, and 1000, they are in the same unit system, kilogram. So in order for you, to think about the force, you gotta know what's going on. So your force is your mass and then your acceleration. Now you do not have acceleration. Yes, you are given velocity. So therefore we're gonna write it in terms of velocity, which is a change in velocity divided by change in time represent acceleration. So now we can see the velocity. We know the differences in velocity. So when you look at it, your force and the velocity, they are, when you look at it, the mathematical equation, they are directly proportional to each other. So meaning like the force will go up when the velocity go up. Okay, and now the problem already told you that the time is the same, so therefore you only have to recognize the mass and the velocity. So that is 8 and 2, so that's about 16, and that is 14 and 1, so that's 14. This is 10 and 15. Okay, is going to be like this. Okay, and this is going to be 12. Because this is 0, 0, 0. Okay, and here 1, 2, 3, 3, 0 again here. And here 16. Okay, and you also have the 3, 0, 0 here. Of course, in this one, when you go, you have 1, 2, 3, 0, 0 here, and then 15 here. So you have 15, 12, 14, and 16. All 3 0, 0 is the same. So therefore, this is the highest. So you got that. The slowest one, when you look at it, this one is the least. And of course, followed by 15 is after 16, and then 14. So you can write it down here after calculation. So you can be able to see this very, very clearly. Okay, we get rid of the t because your problem set is the same t, so that's just one. I just assume it 1 second. If you can make it whatever you want because it's the same thing anyway. And then you have your mass. The mass is given to you. Your velocity is given to you here, and all you do is multiply. Because it said so. Your force is mass time velocity divided by time. The time is the same, so you can cancel them out when you compare them. So therefore I came up with these figures, numbers right there, and then I rank it because it said so to rank from the greatest to the least. So that's the greatest, that's the least, and that's in between them. Then we are getting into the third law. So the third law is also very, very easy. So every force that we think about, every force that we understand with the human ability, force always is an action because you are causing a motion on a mass. So therefore there is an equal and opposite reaction. You have to have equal and opposite reaction because in the universe every object is taking a place Either they are staying at a potential energy with a potential energy in a location, or they are in motion, meaning like moving, staying and moving. It said so in the first law. The third law said, okay, they got to have an equal and opposite reaction if you have an action, because every time you have an action, whether they're going to stay in the position or they're going to move along, can happen only in the medium, only in the environment. So therefore, in the environment, there are other stuff like little particles, big particles, everything particle, and it's very much like you in the water. Okay, when you go down in the water, you can feel the forces from the water particle on you, and you have to put effort to go through the water medium. In the air, is a little bit lighter, so you don't feel a lot of pressure on yourself, but there is force, of the medium or environment. So here is your medium. And that medium has a lot of stuff in it, whether it's empty or with inclusions in that space. Okay, it is acting on it. Okay, and then we are going to take only two things out of that, the entire medium, neglect everything else. So we have a one mass and two mass, and each of this body or mass, they are going to exert a force. So this guy is put a force to this moon, and this moon is going to put a force on this earth. Okay, so here you draw with a little arrow like that, okay, acting forces. So the force acted by the earth on the moon and the force acted by the moon on the earth, okay? And we call that equal and opposite reaction. Otherwise, they are not going to be located at that, okay, position, okay? It will be somewhere else if these forces are not equal. You can make it longer, force for the earth, and make it a little smaller for the moon, and your moon is going to go over there. It won't stay at that location, it will go somewhere else. So anyway, so that's the word. Again, the same thing. Here is the object 1, and here is the object 2 is you are lifting this up, yes. So and this thing is taking that position, and you are taking this position because of the force acting on you and you acting on that. Okay, otherwise you will not be in that position. Of course, you can reduce the force that you act on it. When you reduce it, the force that is acted by this object on you will also decrease according to the force that you exerted. Okay, and you can of course feel it. All right, so for every force of action, again, this word is very important, by the way, because if you don't have an action, an object that is staying somewhere will stay. The object that is moving will move in a straight line, without the other forces. And then, of course, if the force is not an action, this is not happening. Okay, so make sure that you understand every force of action, you're going to have equal and opposite direction. Okay, so here is a force of action, and you have an equal and opposite direction. Here, your first situation, they are connected. Second situation, they're off because of this force on it, because of that force on it. Okay, so that's condition 1 and condition 2. In condition 2, you have two forces. They're the same in magnitude, but in opposite direction. So the link broke. Here is your block. A mass is on the block. They are in that situation, okay, which balances this object, balances with that object block, okay? Why? Because this force act on it by that gray object, and the orange object has a force acting on the gray object, which is this guy. So therefore, it is staying in that position, in the space, okay? So here's your free body diagram of the block, and we can be able to see the forces acting on it, and we call that the force. Every force of action, this force is the force of the gray object on the orange block. Weight of the block is the force acting on that gray object, okay? And of course, these are our x's that we use to analyze these forces. All right, consider a beam. All right, here's a beam, and this beam is resting on these two little triangular blocks, and we have to come up with what are the forces that act on the beam. So let's take a look at it. So here is the weight, and here is another weight, okay, and then here is another weight, okay. So this weight is the weight of M, and it's pointing straight down, yeah, and that's your force of action. And this force of action is balanced by these two forces applied by this little two triangle. Triangle 1 is mg divided by 2. Triangle 2 here is mg also divided by 2 because they are in equal size. See, very the same triangle weight and also shape. And that two forces is the action. When you combine it, it's equal to another, all right, force exerted by the bar, which is your the beam, okay, and this is equal to this two combined, yeah. And see the direction, that's 1, that's 2, and this is 3. So if you put it in a very simple number way, you're going to get like that, yeah. So this is a action force and that's a reaction force. They are equal, so therefore it is staying in that position, okay. Now a large truck, and here is, and breaks down out on the road and receives a push back into town by a small compact car as shown, okay. So here, so we have a large truck, it's going to break down out on the road, and then it's going to receive a push. So this car is going to push this truck out, okay, and it will go into the town, but a small compact car is going to push this truck and put it back into the town. So your force again is like this, yeah. So now that car, okay, is going to start pushing the truck, and you're going to speed up, yeah, to get up the cruising speed. So we want to increase the cruising speed, so the yellow car is going to speed up. So the amount of force right here, so in your brain, these things are pop up, yeah, like I am drawing now, that the car applies to the truck is equal to smaller than or greater than the force that the truck pushes back, all right, with. So our third law is every action, all right, has a reaction. So this force, okay, you gotta understand whether when you analyze the push force, then you have to analyze the pushback force by the truck. And since our resultant, yeah, force is going in this direction, you have to determine the amount of this force and amount of that force, yeah. And I would just say like by the yellow car, and then here is a truck, and you're going to compare because our resultant force is going that way because the motion has happened, yeah, the motion is going this way. So therefore you got to compare the two forces and see which one, okay, is greater, yeah. So you understand that the third law, okay, is completely telling you doesn't matter what you do, the action, all right, force is always equal to magnitude, yeah, and opposite in direction to the reaction force, yes. So here equal and opposite, your action by the car and your reaction by the truck, okay, and they equal to each other. Even if we go back one slide, even if it's still pushing the truck and you have a tendency like the resultant motion is going to this direction, therefore, oh, you know, this force got to be less than that. It isn't true, okay. They are equal. The action and reaction, all right, forces are equal to each other, okay. It's a little bit hard for you to understand it because you have a tendency to think the resultant motion is going to that direction, so therefore the FC, okay, got to be greater than FT, okay. But it is true if you think about the combined though, but here is we're starting only on one single axis, okay, which is I would call it X line, you know, I'll just call it a line. So the component force is the one we are analyzing in the third law, not the combined. This is a resultant, okay. Resultant force create the motion of both of them, yeah, but the component force of action and reaction, they are the same and they're happening on one single axis, okay. So here we're going to analyze this situation again. I'm trying to show you what to be careful when you think, okay, And again, your force is not a single thing, it is a resultant and combined. You remember the summation, yeah, and you remember the breakdown of the motion in different axes, okay? And you know that every line, x line or y line has their own different forces on that line, okay? So in your mind, you should be able to see these components of the resultant force, and in there, by Newton's third law, the acting force and the reacting forces, they are equal and they are happening on a component axis or line, okay? So you have to go all the way down to the coordinate axis level to be able to see the different forces. All right. So for the car and truck, which is a correct statement of the situation, and we are given 1, 2, 3, 4 situation here. So the truck moves forward because the car pushes slightly harder on the truck, then the truck pushes back on the car. That's not true, because if you think about it, you are forgetting about the components. Yeah, your situation is here, but every time we study, we analyze on different axes. Okay, so the car cannot move the truck because the truck pushes back on the car with the same force with which the car pushes on the truck. Again, axis. Yeah, where is it happening? So when we do the reaction action, we're concentrating on this axis. The car only pushes the truck forward if the truck weighs less than the car. Of course, if you think about the resultant force, that is correct, yeah, but for the action and reaction, it isn't. So the car can only move the truck if the car's attractive force, that is the force generated between the wheels and the road, is greater than the force with which the truck pushes back on the car. And this is where you can be able to see the components of the force. Yeah. So what I want to show you is another axis right there. So remember the space shuttle example. So you have a pushing force and you also have a thrust right there. And this is what we're talking about, the yellow car. And that attractive force got to be, yes, greater than the force your truck is pushing back, because this force, they are the equal, the same thing. Yeah, for the whole truck and car to move forward, you gotta have this car, another component of the force on the car got to go over this reaction force. Okay, so that's what it is talking about. Alright, then we will get into the next section where the typical forces acting on a body. We will take a look at it. So we have forces. Don't forget the sum of the forces. Yeah, it's always like this, acting on a body. So therefore the body will move with a velocity and acceleration, of course, every time your velocity changes. So now there are forces that always act on a body, such as its weight and forces that typically act on a body, such as the normal and friction forces. So here we listed out your weight, normal, tension, friction, spring, and damping force. So we have 1, 2, 3, 4, 5, 6 of them. Okay, so these are the typical forces and they act on a body. Yeah, weight, normal force, tension, friction, spring, and damping force. And we're going to take a look at each one of them. So first we go back to our weight again, W. Yeah, and here's the table, here's your apple, and apple, this is the center of gravity, is going down with our gravity, and we only know one planet, and that's where we are on, which is your Earth, and it has a 9.8 kilometer per second, and this is your acceleration due to gravity. Because of this gravity force, your mass is going to go down that way, and we call that weight. Yeah, don't forget weight is a force. And then we're going to come into normal force. Normal force always act on a, again, axis. When you look at it on the y-axis, you're straight down. So here you have a weight, and that weight is always, all right, compensated by the normal force, meaning like they are equal and they are in opposite direction, going down, going up here. And they cancel each other. That's why the apple stays on the table. Then tension force, tension. So tension, when you look at it, we always come with a pulley example where you can be able to see the rope and the pulley, and this box is being held by this pulley in the space, and the tension is again, okay, acting this way, yeah, acting on the road where the lifting is happening right here, yeah. So therefore here is a tension, you have a two tension forces, okay, for this situation. So therefore the boxes is going to be successfully hang on this pulley, yeah. So that's your tension force. And then of course we're going to give an example so you can understand what it is. So your elevator right there, yeah, and then it's being lifted up. The elevator is being lifted up with a big giant pulley right there, yeah. So an elevator shaft at a constant speed. So if somebody cut this, we end up, you know, having emergency situation right there. So here's a big giant pulley. It's going to pull up and down, yeah. And of course this is showing you like how it is going. Of course it's doing on a constant speed, yeah. And these cables are very, very strong, yeah. That's where the mechanical human intelligence, yeah, you know, how smart we are, yes. We build these things systematically, and one elevator can stay a long time, you know, 40-50 years without a problem, yeah. If you maintain this setup, yeah, it can stay for a long time. All you do is replace, yeah. As soon as the steel cable and the pulley come into closer to the end of life, you go and replace it, and it's going to go forever, yeah. So anyways, all frictional effects are negligible, and of course in this situation you're going to have an upward force of the cable is right here, yeah, and that got to be greater, equal to, or smaller than the downward force of the gravity, yeah. So you got to understand what is the action and reaction, okay, and how this resultant motion either up or down is happening, okay. So when you look at it, we understand by Newton's third law, okay, your action and reaction on that axis is always equal, yeah. So therefore your weight mg and your upward force F, they are equal. Don't forget it, okay, regardless of your resultant going upward, yeah. So what if the elevator is accelerating upward? You know, make sure that you understand the situation. The very first one is elevator is being lifted up. See this? Yeah. Okay. And then friction again, negligible. Yeah. The upward force of the cable, which is this guy, yeah, and it is equal to the downward force of the gravity. Okay. Don't get caught up with the resultant force. Resultant force is going up, so therefore your motion is going up, but the action and reaction is the same, yeah. So that's where a lot of the students have a confusion, because they usually go into the resultant force, but no, we are breaking the resultant force down into two axes, and we are now concentrating the forces. Remember the forces, okay, in the y direction, yeah. So I'm gonna write it this way, and that's what we're talking about here, yeah. Okay, and then the second one is your elevator accelerating upward, yeah. Now again, the upward force of the cable, and you have to decide again, greater than, equal to, or smaller than the downward force. Now accelerating, you have an acceleration. If you have an acceleration, you have a force, yeah, because of the same elevator has the same mass. So because of this acceleration, you have a force. So therefore it got to be greater than. So therefore it is accelerating up. Okay, go up. And here is your force. Here is your mg, but you have an accelerating going up. Yeah, so therefore you have this. See this extra force, yeah, according to this equation. It's not only this anymore, yeah, and you have an extra which is causing the upward accelerated force. Here, look, you only have that, yeah, and then of course the force. So therefore there's one situation, and here we're accelerating, so there's a extra, see that extra force on it. And don't forget your resultant force is a sum, yeah, of the forces. Then we come into the frictional force, and of course we use a little sub F for the friction force. Your friction force is going to happen when you have a two contacting surfaces. Yeah, so you have a car here, yeah, and then you have a road right there. And look at this, the object 1, object 2 is a road, object 1 is a car. They are in contact. Every time you have a two contacting surfaces, you've got a friction force. Yeah. So here, just showing you, I forgot to tell you, here is your surface 1, and here's a surface 2, which is this match. Yeah. And then of course there's some powder that is going to create the fire if you strike it on this rock. Yeah. So, and that fire is generated because of this frictional force. Okay, ignite this material that can start the fire. Okay, all right. Now, if the surfaces are moving relative to each other, the friction force is called kinetic friction. Yeah. Again, don't forget the kinetic and the kinematics. Kinetics is all about the force that causes motion. Yeah. So now that we have a kinetic friction, yes, the friction that is going to cause the motion, now acts to retard or slow down the motion. Okay. So here, look at this bear, and then the ice. They're in contact. Two surfaces in contact. So if the surfaces are moving relative to each other, the friction force, we're going to call it the friction that can produce a motion. So now the bear is in motion, yeah, because we have the surfaces that are moving relative to each other, and we call that type of friction kinetic friction, the friction that causes the motion. So now this bear is still in motion, yeah. So that type of friction will either retard or slow down the motion. Okay. So if the surfaces are not moving, like this situation, now he is climbing up, yes, up the mountain, to each other, the friction force, we're going to call it static friction, because they are not moving, they're not producing the motion. Yeah, they're trying to balance the moving, okay, object. So you are moving, climbing up the mountain, and here it is going to create a static friction. Friction is because it's acting to prevent that motion that this guy is, all right, exerting. So the guy got to put more energy to go against that static friction to go up. Yeah. So you have to use energy that is going to be greater than the frictional force to make a motion upwards. Example 5.3-2. So now here we're going to think about this block, again mass M, and being pushed along a flat horizontal surface. You want to push it with this force, and you can see it says that this is your flat, and it is definitely horizontal surface. So what, okay, forces are acting on the block? We got to come up with the forces, so you know that there's a first force, yes, and that force is again, yeah, creating motion going in this direction. See, there's a motion arrow showing, yeah, the motion happened because of this force. Yeah, so therefore when you draw the free body diagram, you've got to put everything in it. The very first one is the weight of that mass. Second one is the reaction of that weight, okay, which is happening on the y-axis. And the next one is the force, the pushing force, and the friction force that is resisting that force. Okay, so action, reaction, action, reaction. For this to result in there, that guy gotta be greater than, okay, the frictional force. So therefore the resultant is going this way. But you have other forces, okay, which is your mg is equal to the normal force, and that is happening on the y-axis. This is happening on the x-axis, and we have a bigger, stronger force. So therefore the entire, okay, block is going to go this resultant force going that direction. All right, and then of course we write it here, some of the forces on x, yeah, line, and the y line is here, is going to be like this. So you can subtract the frictional force here acting on the object, and you're going to get the resultant, okay, going in this direction with a particular acceleration, okay, which is causing that force. All right, spring is the next force, typical force, And you can see three situations here for the spring force. The very first one is taking a distance, it's go down here, and we usually write with kx. And then of course the second one go up, so you have a different distance that this spring is going up and down, yeah. And then of course you can pull it, and it's going to go all the way up, and you can see this distance, okay. And when you release it, it's going to come down because it is a spring, yeah. Again, that release force is going to be Fs is equal to K and then X. Yeah, this is just a typical equation that we write just like your F is equal to ma, but for spring force, we usually write it with F spring force is equal to K times X, and this X is going to, okay, represent the distance of the spring that can go up and down, yeah. All right, a damping force is going to be D for damping. So every time you see your force with the sub D, we know that we're talking about the damping force. So here is the extension, yeah, cycle here, and this is your piston, the whole thing, and you can see the lower mount, your base valve, and then your pressure tube, and then your reserve cylinder, and then your oil here, your oil piston here, yeah, the piston rod is here, and this is your upper mount, which is take a look at this piston, yeah, and in the mechanical design, and you can be able to see the damping force is equal to C, and then look at this little tiny dot in there, okay, don't forget that. So that's a change of position, which is your, yeah, CX, and there's a little dot on it, yeah, so it's showing you the extension, and then the compression cycle where it's been pushed this way, extension has been pulled out that way, okay. So we have a two cycle, extension cycle, and then the compression cycle, and make sure that you understand the direction for extension, all right. You're going to have a reaction forces pulling that way. For compression, since your force is this, you have a reaction that way, okay, since your resultant force is this way. Okay, what I'm going to do is I am going to stop for the second part here before we get into friction, yeah, friction and damping force. We will come back to this too in details, okay. Of course, you don't really need to know for calculation because I'm teaching you how to do the MATLAB, and by this time you should be able to program your equation, yeah, in this application, your MATLAB platform online. So let's go ahead and stop here.